Welcome back to the Yellow Submarine Testing Chamber at the ITIS Foundation in Zurich. This is episode 2 of the Implant Safety Testing Series, where I show you how to characterize active implant medical devices per the ISO TS 10974 standard. In the last episode, I showed you how to characterize a device with the PIEX system, where we made a model of how the implant responds to incident fields in tissue simulating liquids. Today, I'm going to show you how to validate that model by exposing the implant to different incident fields and testing if the response matches the prediction that we get from the PIEX model that we made in the last video. Since the last video, I calibrated the PIEX model by measuring the exposure under an incident condition. This is easy to do. You can pick any incident condition you want and just measure the field proportional to the background, or the SAR enhancement. I'll be validating the PIEX models of the SAMDU validation device, which we measured in the last episode. As last time, I'm going to be measuring the implant response at the tip and the induced voltage inside the can using this 2-port connector. I'm going to be doing the measurement at 64 megahertz, but you could do it at 64 or 128 with the MITS 1.5 or the MITS 3T. Traditionally, people validate the model of their implant response by mounting the device inside a phantom such as this ASTM phantom and physically varying the routing of the lead in order to change the incident field conditions. Many routings are necessary in order to achieve sufficient diversity of the incident fields. Today I'm going to show you the test field diversity system that we've developed together with Zurich MedTech. We use a large cylindrical phantom, which we expose to a wide range of incident field polarizations in the MITS. We place the implant along a set of defined routings to create diverse incident field conditions along the implant. We have 6 different options for the routings that we've used so far. So one is an oval shape, like this. One is an S shape, like this. And one is an E shape, like this. Each routing can be used clockwise or counterclockwise for a total of 6 possibilities. However, as Aiping Yao showed in her thesis, only 2 routings are necessary to robustly validate most implants. For this video, I've affixed the implant along the E-shaped routing. You start with the tip at this defined point here, and then you route the implant around as long as it takes until you get to the can. You can accommodate a system up to 110 centimeters in length by using the whole length of the routing. Next, I'm going to connect the RF over fiber voltage probe and show you how we've calibrated that. Before I connect the RF over fiber probe to the SAMDU, I need to measure the sensitivity of the system to incoming voltages. I connect it to port 1 of this VNA with the RF over fiber calibration unit, which is a special adapter with a known loss. The RF over fiber unit is connected by fiber optic cable to the remote unit, which is connected itself to port 2 of the VNA. I've set the VNA up to measure the S21 at 64 and 128 megahertz. It has a very flat response, and I'm looking at minus 45 dB. What that means is that when I measure something with this, I take the number that I'm measuring, which is the input power, I subtract that number, so subtract 45, I subtract 10, which is a conversion factor, and what I'm left with is the resultant dBV. The Medical Implant Test System, or MITS, has the ability to generate the same incident field as commercial scanners, but we use it mainly to generate well-defined incident fields, which we use to calibrate and validate our implant models. The test field diversity phantom is a large cylinder here, which generates well-defined incident fields, 2 of routings that we've defined with our racetracks. The incident fields for each polarization along these defined routings was numerically derived and experimentally validated for each of the tissue simulating media defined in ISO TS 10974. Today I'll be using 0.47 Siemens per meter tissue simulating liquid, the same as we used in the episode 1 with the PIEX model, but you could also do this at lower or higher permittivity liquids. I use the portable dielectric assessment kit, or DAX, from Speag to check the conductivity at 64 or 128 megahertz. The time domain sensing B1 system uses 2 orthogonal H-field probes, which are sensitive in the X direction instead of the Z direction, to measure the polarization ellipse of the MITS. This special holder keeps them orthogonal and helps you to raise and lower it such that it comes to the well-defined spot inside the TFD phantom, which we can correlate to our expectation of the induced field from each polarization. This allows us to experimentally validate each polarization that we've set in the MITS software. I made a separate video that showed in more detail how this works. You won't see much of it here because it's fully automated in the DAISY workflow. But you can watch that video and see how these two fields together capture the polarization ellipse of the MITs for each incident polarization that we use. This is the MIT software. I'm running a square wave with a 40% duty cycle and 43 dBm, or 20 watts. Normally, one would let this simply auto-calibrate to find the linear polarization. But today, we're going to be doing the TFT measurement, which means that we're running through these 20 predefined polarizations. These are epsilon tau values corresponding to different polarizations that can be achieved by the MITs. The colors in this graph represent the potential enhancement from isoelectric of the implant at each polarization. You can see that this is a polarization that results in a relatively high deposited power, and these are polarizations that result in relatively low deposited power. These 20 numbers indicated in green are the polarizations that were selected for this MITS, for this routing, in order to sample the whole dynamic range possible by the implant. For each of these, we have a DAISY file where we measure the TDS V1 value at that polarization, and then measure the point SAR above the implant at a defined spot. Next, I measure the volume scan for the polarization with the highest SAR. And after the measurement is done, I measure the background E field along a 20 centimeter reference line for each polarization. Then the data are processed by scaling the field to the appropriate amplitude from the background scans, and the volume scan is used to relate the point SAR measurements to the deposited power, which we then directly compare with the predicted values. For the induced voltages, of course, the measurements are just compared to the incident field directly. These are the 20 polarizations that we've measured as the 20 test configurations. As you can see, the agreement in deposited power in milliwatts between the radiated test and the predictions of the pi-x are very good over the 20 polarizations. The deviation is well within the uncertainty. I just showed you one measurement set, but repeating it with a second routing is a fast way to get even greater field diversity. That's how we get a validated transfer function. It's very fast and easy. As a next step, we're working with Zurich MedTech to automate the evaluation process using the power of IM analytics. But meanwhile, that's it for episode 2. In episode 3, I'll show you how we extend the transfer function concept beyond homogeneous media using the so-called tier 4- approach. Thanks for watching and see you next time.